On tonight's show, I conduct some serious scientific research, Liz tries to answer the nature versus nurture debate, and Jem tries to power a helicopter with a microwave oven. That's Bang Goes the Theory, putting science to the test. And welcome to Bang Goes the Theory. Now then, science doesn't get any more tricky than the hunt for dark matter. Basically, Newtonian physics is in trouble. Dark matter. The missing chunk of the universe is one of the biggest questions in science. So big that it needs cosmologists, JCBs, parachutes, and one gullible presenter to explain it. Nice forehand. Until recently, the way the universe worked was so simple you could explain it all with a bat and ball. There we go. According to Newton, the Earth wants to whiz off into space, but the gravity of the sun pulls it back. The result is the two forces balance each other out, and the Earth orbits nice and steadily around the sun. So, thanks to a bit of clever maths from Sir Isaac, that's space sorted. And his laws didn't just apply to our solar system, it's how the whole universe is supposed to work. Well, so we thought, until we invented some very big telescopes and began to look at some distant galaxies. What we found was that they behaved a bit like our solar system, with all their billions of stars orbiting around the centres of their galaxies. But then we realised that the stars on the edge were misbehaving. They were going too fast. Let me illustrate with the help of a cosmologist called Dr. Kukula and a very big digger. So you're at the centre of our galaxy, yeah?
I'm the black hole at the centre of the galaxy.
OK, perfect. Imagine I'm a star right at the edge of our galaxy and I'm sort of spinning round. How fast exactly am I travelling?
You're probably moving at about 70 or 80,000 kilometres per hour.
Quickish.
Pretty quick, yes.
All right, start your engines. What this test represents is the forces on a star spinning around the centre of its galaxy. OK, so far so good. Just like in the ball game, I'm being held nicely in orbit by gravity.
Whoa! So what's the problem?
When astronomers measured the speed of stars whizzing around the centre of their galaxy, they found that the stars were just moving too fast.
Star going too fast!
They couldn't see enough stuff in the rest of the galaxy to provide the gravity you'd need to hold the stars in their orbit. So they should just go spinning off into space.
Oh, God!
Here's what I don't understand. It's because stars are still travelling at this amazing speed and they're not flying off, being ejected into deep space like that.
No, they're not. They seem to be orbiting quite happily around the galaxy.
So it must be something else.
There is something missing, and this is what we call dark matter. It's what we need to provide the extra gravity to hold the stars in their orbits. And so we need to find out, otherwise we'd have to rewrite the laws of physics, and we'd really rather not have to do that.
Scientists have been looking for those strange particles of dark matter for years now, and they found nothing, absolutely nothing. So does this mean the scientists have made this dark matter stuff up? Well, no. Because it interacts with almost nothing, we'd only know if a particle of dark matter was anywhere near us if it hit the centre of an atom that we just happened to be watching. And how likely is that? To paraphrase my hero Douglas Adams writing on the nature of matter, the chances of this happening are very small, roughly comparable to that of dropping a ball bearing at random from a cruising 747 and hitting, say, an egg sandwich. didn't have a ball bearing, so I thought I'd use myself. Okay, let's go. I am on. We think of things as solid, but at the atomic level, they're really not. If our egg sandwich was the size of an atom's nucleus, and I was a dark matter particle, then pretty much all the ground you see beneath me would be space, which I would whiz straight through. But I'm going to do what dark matter particles can't do. I'm going to aim straight for the nucleus.
There it is, egg sandwich, 12 o'clock. Oh, close! Oh.
We're so nearly, I mean, look at that, we were right on it. I reckon with a couple more goes, we will nail that.
I love that film, I absolutely love it.
But you know what? I know he cheated and used a dummy Dallas on the JCB. I built the release rig. And it's a good thing he did cheat. Watch this.
Okay, but let's get back to Newtonian physics for a bit,
Right.
shall we? All right, we're going to test gravity. Now, you probably think of gravity as a force that makes things fall, okay, like the apple on Newton's head. But gravity is actually a force of attraction between two objects of mass.
The fascinating thing for me about gravity is even though we understand it, we can make great mathematical predictions about what it's going to do, we don't really know how it happens.
No, but one thing we do know is if you drop an object on the Earth, the object and the Earth will be attracted to each other. It's just the Earth moves so incredibly slowly that for all practical purposes, it's the object falling to the ground.
But that doesn't mean if here on Earth we drop two objects from the same height, they're going to land at the same time, because it's not the only force at play.
It's not, and that's the really interesting bit, isn't it? Dallas, are you ready?
I am ready up here. Okay, this is a classic experiment. I've got two identical bottles here. One is full of liquid and it's very heavy. The other one is almost empty. There's a little bit of water in there just to keep it stable on the way down. Now, if I hold them at exactly the same height, on 3, 2, 1...
Way!
Nice one.
Yeah, well done you. Now, the full bottle definitely landed first there, okay? And that's because air resistance is another force at play here. It works on all moving objects around us, and it was the same on both those bottles as they fell to the ground. But the full bottle built up more momentum because it was heavier, and it was able to push against that air resistance more, and it landed first.
Exactly, Liz. Now, if we did that same experiment somewhere where there was gravity still, but no air resistance, then they would fall at the same time, or at least they should do. Now, a good place to do that would be the moon, and we sent a couple of chaps up there to test it out.
How about that? Mr. Galileo was correct.
It was very good of them to go all the way up there to do that for us, so thank you very much indeed. Luckily, it worked.
Otherwise, we would be rewriting the textbooks.
Exactly.
Okay, let's move on, shall we? When it comes to the difference between boys and girls, you guys, do you think it's nature or nurture?
Oh, no, boys are just born different.
So you're saying nature?
Yeah.
What about you, Dallas?
Oh, it's a good question. I'm going with nature, I think.
All right, well, let's take a look at this because you might be surprised. By 15 months, most boys seem to like playing with cars and machines, while most girls seem to prefer playing with dolls and so-called girly toys. But is this down to our genetic makeup or is it learnt behaviour? To find out who's boss in the nature versus nurture debate, I've come to Cambridge to conduct a little experiment that puts the nurture argument to the test. Volunteers are each given a toddler to look after. They think they're taking part in an experiment to see how babies react to strangers.
Now, what our contributors don't know is that they are actually our guinea pigs today and not the babies.
How will the adults react when presented with a boy?
Hello, Caleb. But we've got some toys to play with if you want to play with some toys. Or maybe you want to play with a truck.
Okay, so questions just picked up. The red fire truck.
Some toys until...
But what our volunteer doesn't know is that Caleb isn't a boy. She's really a little girl called Kaylee.
Make him look just like a boy. A boy. A boy.
want to play with the helicopter? Yeah, you want to play with the helicopter. Do you want the truck as well?
The helicopter's a hit. Regardless of the fact that Kaylee's a girl.
In fact, when presented with a toddler, all our contributors opted for the gender stereotype toy. James, dressed as a girl, clearly makes his feelings known, but our guinea pig keeps on trying. And it's not just our guinea pigs, because almost all adults will give boys toys like trucks and tank engines to play with, and will give girls nice pink fluffy toys to play with. And apparently it's the boys that have the hardest time of it, because adults are much more keen to discourage boys from playing with dolls than they are to discourage girls from playing with cars. What this experiment shows is how likely adults are to gender stereotype, and therefore how easily they can influence our children. But just because adults influence children doesn't necessarily mean that nature doesn't play a role. I've come to Woburn Safari Park to illustrate a controversial experiment that still raises eyebrows many years after it was first carried out. Its creator was Dr. Melissa Hines.
Some years ago, I wanted to find out if I could find a group of children who hadn't been socialized to choose different toys, and see if they still gravitated towards toys that were for their own sex. And try as I might, I couldn't find such children.
So Dr. Hines had a radical thought. Why not experiment with monkeys? They obviously don't normally play with toy cars and dolls, so any toy preferences can't be down to the influences of human society. Keeper Laura helps us illustrate Melissa's experiment by setting out the toys for our unsuspecting monkey audience. And it's not long before the nature argument appears to kick in.
Who's that on the helicopter now, Laura?
That's Frank.
Excellent. And now he's chewing it.
That's probably Jaffa, because he's the oldest baby.
Well, Jaffa,
And
the
he'd be
baby,
born
went straight
Christopher.
for the yellow truck.
Incredibly, despite the small sample size, the monkeys seem to show a gender preference for the toys.
Who's that there now?
That's
Laura?
Blondie.
Blondie's a girl, I take it.
She is, yeah.
Blondie
fairly-
walked straight past the truck.
Although this is just an illustration, what we've seen closely matches what Dr. Hines discovered.
On the average, the male animals spent more time with the boys' toys than the female animals did, and the female animals spent more time with the girls' toys than the male animals did.
As if to prove the point, whilst our backs are turned, there's been a bit of monkey business.
Baby! Pink baby out of the bag! Pink baby monkey.
True to form, Gara has gone for a girly toy.
Where did she get the toys out
But
of?
they were in the bag
That is
still.
so incredible.
Let's look.
This is amazing, right? We're focusing on all these monkeys, but behind the truck we left a bag of unused toys. Gara, a female macaque, went into the bag, rummaged around, and stole this pink cuddly monkey toy and ran up the tree with it. That is so cute.
That was brilliant. Now, here's my question, though. I can understand why girl monkeys are going to want to play with dolls and the like, but what is it about things like helicopters, trucks, cars that is so attractive to boy monkeys?
Yeah, good question. Well, if this is part of our evolutionary heritage, then all this would have started before there were any vehicles around,
Exactly,
right?
yeah.
So what scientists think it's down to is that males are attracted to things with moving parts, like mechanical objects, and that they're attracted to motion, basically. And that's why you saw the monkeys there spinning the wheels.
Yeah. But where are we then with the kind of nature-nurture debate? I mean, is there a conclusive evidence either way?
Well, the classic scientific view was nurture. It plays a
Right.
huge part on your preferences like like we saw in the film. But more recent research has shown that nature plays just as big a role. So I'm sorry to sit on the fence with this, but it actually is a very big combination of the two.
That's okay. I mean, that kind of makes sense, I think.
Yeah.
Talking of monkeys spinning wheels, Dr. Yan is having a little bit too much fun.
I've challenged these people to try and see if you can make yourself spin on the chair. In fact, try it at home, but feet off the ground and you're not allowed to push off anything. Harder than you might think. Yeah, you're putting your feet on the ground though. So I reckon with a bit of scientific know-how, we should be able to do better. This is just a normal bicycle wheel. And if I make it spin fast, in fact, really, really fast, then I'm giving it lots of spinning momentum. And now, watch what happens. Whee! Just what we couldn't do before. Whee! Right.
Oh, that feels really weird.
Try turning it the other way. Whee! Whee! This actually illustrates one of the most fundamental principles of the universe. When I change the wheel's direction of spin, it changes my direction of spin. And that's because it's giving me some of its momentum. It seems really weird because we're not used to it. We don't normally move spinning objects about like that. But scientists and engineers use it quite often in things called gyroscopes. Oh, there we go.
Now, there's been an awful lot of research recently into new sources of energy, and I felt I had to get in on the action.
Funny that.
There's actually a vast amount of invisible energy consistently beaming through the air around us. Radio waves off masts like that over there, television signals off similar masts, even microwaves sending information to our mobile phones. In fact, the rays of the setting sun over there, they're all examples of one special kind of wave, the electromagnetic wave. It should be possible to harness the energy from these waves. And there is a way of extracting electricity directly from electromagnetic waves by using an aerial or a piece of wire. I've attached my length of wire to a small LED, and my source of electromagnetic waves is a standard CB radio. When I press this transmit button, I'm going to start sending out some pretty low power radio signals. But if I've got the length of my wire right, I should be able to convert them into enough electricity to light this LED. Seems unlikely, but here goes. Yes! Look at that! This is, honestly, it's not attached to anything at all. There is no electrical source going in here. Just what I'm making from the radio waves. But a little CB radio is never going to get a helicopter off the ground. I need a source of electromagnetic waves with more power. Luckily, in the workshop, I've got one that can melt glass. It's a microwave. This is only 4 watts. But this has got 1,000 watts of microwave power. Now I need to convert it into a giant energy transmitter, a sort of microwave ray gun. And like anything involving ray guns, this is dangerous work. Any of that could kill you. Even though this microwave is unplugged, the electrical charge is still in there. That means it can give you a massive belt that could kill you any time. And that is the magnetron, where the microwaves are actually produced. So really never take these things apart. Now for the fun bit. I'm making a funnel to concentrate the microwaves in one direction. There's easily enough power focused through this to fry my eyeballs. Wow, I hope I've done the right thing here. In the wrong hands, that could be described as a microwave death ray. In the right hands, hopefully it's a device for beaming invisible power. Now, I would dearly love to turn it on here and now, but I can't, because A, it's utterly illegal, and B, it could not be more hazardous. But I can turn it on here.
This quarry is an ex-Ministry of Defence testing site, and we still needed a special licence to use this thing here, and only then if we monitor the radiation with one of these. Now meet Sam. He's a top young pilot. He's going to take care of flying the helicopter whilst I monitor the microwave situation and take us through the science. If we're going to collect electricity directly from microwaves, we'll need an antenna, just like the wire I used to get radio waves to power my LED.
But microwave technology is super fiddly, so I've had an expert called Julian Workset make us this, an array of microwave antennas. It looks complicated, but it's effectively just made of 100 short wires, called dipoles, which are tuned to my microwave beam. The precise spacing of the dipoles is critical, and very few of these antennas have ever been made, so we're wading into a world of trial and error. Hopefully, not so much of the error.
From here will emerge a beam of microwaves. They'll travel at 186,000 miles a second until they reach here, our antennas. Now, the microwaves are going to set up a voltage in each of these antennae. The voltages and currents are summed up at the back here, and as electrical power, it comes down that wire to that helicopter. Here goes. Let's see what happens. Okay, couple of minutes of flying time. I'm going to switch the microwave on now. I'm just going to check that we're safe standing here. Stand back a little bit just in case. Yep, we're good.
Now to slowly angle it down at the antenna. I don't want to fry the components on our first go.
We're now beaming maximum power at the antenna, so we should start getting a bit of a voltage appear there at the helicopter. Now, it's quite a powerful little helicopter, so I don't know if it's definitely going to fly.
We have power. Now, is there enough for liftoff?
Yes!
But there is a problem. No matter what we do, the power levels are just too low to lift the helicopter and the wire. Still, we proved the point. We can get electricity out of thin air.
High five. It's managed to send enough power to a helicopter to actually lift the helicopter clean off the helipad. I'm astonished that that technology actually works. So, bring on the future.
I just think that is astonishing. You are like every member of the A-team rolled into one package. But you did say earlier on that you were going to try and harness new energy.
Yeah, I used microwaves in that film because they're of about a 12 centimetre wavelength, which means we can make aerials the right kind of size for collecting the electricity. Okay. But in the future, the idea is to harvest electricity from electromagnetic waves that are much, much, much smaller. Say hello to infrared.
Our microwaves were harvested from energy sources created on Earth. But if we could capture infrared, we'd be getting free energy from space.
Infrared is invisible to human beings, except if you've got one of these cameras. Now I can see.
This is tuned to the infrared spectrum and clearly shows it coming off the crew and me.
The heat of my body causes me to radiate infrared waves the entire time, but I'm nothing special. Anything with a temperature above absolute zero is always emitting infrared. You've seen how we collected power from invisible microwaves being beamed through the air. Now imagine the potential of being able to farm electricity directly from all this infrared. But infrared waves are tiny, less than 1/100th of a millimetre long, and no one has been able to build an antenna that small until now. I've arranged to meet the man who's built the world's first large-scale infrared antenna.
His name is Steve Novak. The technology is so new that there are only 2 prototypes in existence.
It's one of the most exciting pieces of technology I've ever heard of. This could actually change the world.
And he's bought the antenna from his labs in Idaho to show me.
Hi, Stephen.
Hi, nice to meet you.
Nice to meet you. Thanks so much for coming. So, can we have a look at it?
Oh, absolutely.
Is it this sheet of plastic?
That's right.
Okay.
Rolled it.
And that's the infrared antenna?
That's correct.
It's not like I imagined it looking, but I guess there's more to it than first meets the eye.
This is essentially a miniaturized version of our array of microwave antennas.
Each one of these 4-inch squares holds about 260 million antennas. So the 3x6 has about 4 billion.
4 billion antennas on here. And they're all like of the right length for collecting infrared waves and turning them straight to electricity.
That's correct.
Wow.
These antennas are so efficient that they can point in almost any direction and still collect infrared energy from the sun.
And what about on a cloudy day like this?
Well, if you collect the right wavelengths, the infrared should get through the clouds and should have no problem there.
So you can pretty much get as much on a cloudy day as a sunny day?
That's correct.
Oh, this stuff's better than I thought.
What's more, these panels can also collect the infrared given off by the Earth as it cools at night.
Solar panels that work at night?
It does work at night.
Incredibly, the Earth emits so much infrared at night that a 1 square metre panel of Stephen's antennas could light several light bulbs.
That's it for this episode of Bang Goes the Theory. We'll see you very soon. Shall we say goodbye?
Let's say goodbye.
See ya.
Bye.